So hello, today we're going to look at example problems for chapter 26. Chapter 26 is mathematically a pretty straightforward chapter equation-wise. All of the equations I have displayed in the upper left are about reflection and refraction. Really, the tricks to chapter 26 only comes in when you want to really start messing around with geometry. But for now, well, we'll see what we got. I'm just going to start solving them. So, the first one, light rays from the sun, which is at an angle, that's horrible English. Light rays coming from the sun, which is at an angle of 35 degrees above the western horizon, strike the still surface of a pond. And so what I have, pond, is I have some water, and I have a light ray coming in. And it says this light ray hits it 35 degrees above the western horizon. That means this right here is 35 degrees. What is the angle of incidence? The angle of incidence is always the angle from the normal. If this is 35 degrees, we don't actually care about that. We want this angle here. And to find that angle, that's just, well, this is a whole right triangle. It's just going to be 90 degrees off. Oops, I can math. Pay no attention to the fact I failed at math. And so the angle of incidence is 55 degrees. That's what we care about. And it says, what's the angle of reflection of the rays that leave the pond surface? And all we're going to use is the law of reflection. The angle of incidence equals the angle of reflection. If this comes in at 55 degrees, and let's do a slightly different color as it comes out, it comes out at 55 degrees. That's the general idea. Then it says, in what direction and what angle from the pond surface are the reflected rays traveling? I didn't write this problem. I think it's kind of a weird thing to say, but it's that way. It's coming out, if it's coming in 35 degrees above the western, we could say it's coming out 35 degrees above the eastern, or we could just say that it's 55 degrees oval, traveling in the opposite direction.
Quick question.
Yep.
Would that be a problem on one of our exams? Just say which.
No, I'm not that neat. I don't do that simple. I'll pull up last semester's exam when we start reviewing, and you get to see what I did. Probably I'll do something involving a few more pieces. I'll give an example. One of the other ones we're going to do today will be closer, but I'll give you examples of the type of thing I could do. There's a small mistake in the solutions that I'm fixing right now. But that's it. That's kind of all there is to it. Okay, fixed the mistake in the solutions. There's a typo though. Next one. The index of refraction of Sophia's cone. This is when you use textbook problems. It's just like, we're going to talk about Sophia's eye. Who the fuck is Sophia? No idea. But we're going to talk about her eye. Say, the index of refraction of Sophia's cornea is 1.376. And that of the aqueous fluid behind the cornea is 1.336. Light is incident from air onto a cornea at an angle of 17.5 degrees. What angle to the normal is the eye traveling in the aqueous fluid? Now, where this came from the textbook, it didn't even have this picture. I kind of added it. No, this picture is from it. But what it says is light's coming from the outside. It's going to hit the cornea and then go through the iris. That means if I was to make this bigger, we're going to say we have an area that's an air where n equals 1. Light then hits the cornea where n equals 1.376. And I'll just call this 1, this 2, and I'll call this 3. And then it goes into the aqueous fluid, which is 1.336. And these are actual numbers for the eye. And we're going to say that light comes in at an angle of 17.5 degrees. That means this light comes in at angle 1 with theta 1 equals 17.5 degrees. And if I want to find what angle it is coming through here, I'm first going to have to figure out what angle it is here, theta 2. I can only do one change at a time. I can say going from 1 to 2, then from 2 to 3. Now to figure this angle, I'm going to use Snell's law. N1 sine theta 1 equals N2 sine theta 2. That means the sine of theta 2 is N1 sine theta 1 over N2, which would be 1 times the sine of 17.5 degrees over 1.376. And doing that math, I get the sine of theta 2 is 0.2186. And taking an inverse sine, that means theta 2 is the inverse sine of that, and theta 2 is 12.62 degrees. Now that gives me this angle theta 2, but here's the thing, is I'm going to hit this guy and bend again. And I'm going to have to say, okay, now here's my normal. But what we know is if I have two parallel lines, if they were divided by any line, the inside angles are the same. And my normal is going to be the same. It says to ignore the curvature of the eye. That means that angle theta 2 is the same as this angle. That's also theta 2. And the answer I'm looking for would be theta 3. And we'll just say N2 sine theta 2 equals N3 sine theta 3. Sine theta 3 equals N2 sine theta 2 over N3. Or 1.376 sine of 12.62 over 1.336, which is 0.2251. And therefore theta 3 is the inverse sine of 0.2251, or 13 degrees. And there you go. If it hits your eye at 17.5 degrees, it's going to be going into the back of your eye at 13 degrees. Each time having an angle shift as the index of refraction changes. That's the general idea. It just kind of, you do it piece by piece. Questions?
Nope.
This is still a little simpler than something I'd put in an exam. The one I had last time involved some reflection and some refraction and some other stuff. This guy right here is probably closer to the type of thing I would do on an exam. Although this one might be a little complicated geometry-wise. But as it's of the ones I'm doing today is the closest. Side note, last semester's exam is on Banco Hall. You can already look at it. So if you want to see what I did, or last year's exam, if you want to see what I did last year, you can go see. I have to start writing this year's exam. Okay, so I am going to draw all over the figure here instead of doing it on my paper, so I have to draw it again. And it says, a light ray traveling in air is incident on one face of a right angle prism with index of refraction of 1.5. So I'm going to say N1 is air, N2 is 1.5. And the ray follows the pattern shown in the figure, assuming theta equals 60 degrees, so you can randomize it, and the base of the prism is mirrored. Determine the angle phi. Okay. So I got to work out all these angles. And the first one I got to figure out, let me grab my annotation. All right, let's not do blue, it'll blend in too well, is this angle, because that's going to be the angle it enters in. And that's not immediately obvious what that angle is going to be. But I say that if this is coming straight down and making 90 degrees, as we show here, I can try to figure this out. And how I'm going to do that is I can say this angle. You know what? I'm going to do something different here. I'm going to basically make this big. So if this is true, I can say that this angle, which I call it alpha, I'm just arbitrarily picking things, I can solve for that angle. And I just realized I need some room for text. I can say that's alpha because what I'm going to do is I'm just going to say that that's the I can make I'm making a triangle here where I have also right. And we know in any triangle the sum of the angles is 180. So I know, well, can I see what I'm writing up here? I know alpha plus theta plus 90 equals 180. And I said theta was 60. So alpha plus 60 plus 90 equals 180. So alpha equals 30 degrees. Now that I know that, I can say, okay, if I look at just this blue line, and if basically pretend it was continuing through, I can say that I have the angle between here and here must match the angle between there and there. Did I actually do that like that? I'm trying to see how I did it. Yep, I did. And so I can say that if this angle is alpha, must be the same as this angle. And so if that's 30, this must be 30. But I got a whole 90-degree here. The angle it comes in, what I'm actually looking for, theta 1. Theta 1 plus alpha is another 90-degree angle. And therefore, theta 1, what I actually need, is 60 degrees. Now that I have theta 1, I can get theta 2. That was amazingly well-drawn theta. And to get theta 2, I'm just going to use Snell's law. I'm going to say n1 sine theta 1 equals n2 sine theta 2. Which means theta 2 is the inverse sine. I'm just going to do it in one step this time because I'm trying to do it in a small amount of space. Of n1 sine theta 1 over n2. And plugging in my numbers, 1 times the sine of 60 over 1.5. I don't know if you guys actually need to see me plug in those numbers. I'll get that this is 35.2 degrees. Now that I have theta 2, I got to deal with this reflection. Now, how I'm going to deal with that reflection, sorry, I'm just checking what I did, is what I'm going to do is I'm going to say if that's theta 2 is that, I want this angle, but I have a nice triangle left right here. And this triangle has an angle of what I called gamma, 90, and this guy here. But this guy here, well, I don't know what that is yet. I gotta have to figure out what that angle is. But I can see that alpha plus theta 2 plus that mess is going to be this angle here. And actually, did I not use that one when I did it? Sorry, I'm reading my solution real fast. I went straight from theta 2 to gamma. How? Oh, because I went straight to. Sorry, I think there's actually a mistake in my solutions. So I'm just quickly checking my math. 90 minus theta 2. What's that? Oh, I see what I did. I see what I did. In my solutions, I didn't use that triangle. It doesn't really matter, but I used this one. And I said that this whole thing, this angle here, alpha plus this mystery bit that I don't care about, really? That's just going to be 90 minus theta 2, that top bit. And so I'm going to say 90 minus theta 2 for that being, switch colors, that being this, 90 minus theta 2, plus theta, which is, that's just the regular theta, that's my 60 degrees. So let's just call it 60 to not cause a mess. Plus this angle gamma that I was talking about must equal 180. And I can plug my numbers in there and I can get gamma. That gamma is 65.3 degrees. So that's this angle, but I want this one here, which I called theta I, because it's going to be the incident once they start reflecting. Because I'm about to have a reflection. But theta I plus gamma is 90. So theta I is 90 minus 65.3 degrees. And so we're going to get 24.7 degrees. That's theta I. Any questions so far? I'm kind of going all over the place, and I acknowledge that. Well, as I said, when these get messy with geometry, they get messy with geometry. This is harder than I'd put on the exam. But if that's theta I, it's reflecting. And we know the angle of incidence equals the angle of reflection. And so if that's theta I, I'm just going to slide off to the side, that theta I equals theta O. And so theta O is also 24.7 degrees. Now it comes up and bounces and goes out the other side. But then I'm left with, now I need to know what this little angle is, which I called theta 3. And that's not immediately obvious either. But what I'll do is I'll once again make a triangle. I'll say I have a triangle that consists of, and let me erase my other triangle because I don't need it right now. I'll say I have a triangle going from here, ooh, that was a horrible line. From here, here, there. I'll say I have that triangle. Well, this is 90 minus theta, so this is 30 degrees. This guy, I'm not quite sure what it is, but this one here, if everything's bouncing off the same, that's going to be the same as gamma. That this will still be that same angle, just because if this is gamma plus theta 1, and this is gamma plus theta I, and this is gamma plus theta O, and theta I and theta O is the same. So this gamma was what, 65.3 degrees. I can find this top angle, which for the record, I called epsilon because I'm just making my way through Greek letters like there's no tomorrow. And I'll say 180 equals 65.3 plus 30 plus epsilon. And doing that math, I can get my value for epsilon. That epsilon, what did I find epsilon? Is 84.7 degrees. Now that I got epsilon, I can get theta 3, because epsilon plus theta 3 is 90. So 90 minus epsilon equals theta 3, and that's going to be like 5.3 degrees. And now we can finally get to the end, because I'll just Snell's law again. I'll say that n2 sine theta 3 equals n1 sine theta. I'm going to call it theta full for no apparent reason. Oh no, they call it phi. That's on the figure. And so the sine of phi is n2 sine theta 3 over n1. N1 was 1, so it'll just be 1.5, the sine of 5.3. Oh, I'm off the, sorry. Yeah. which doing that math, I didn't actually solve for that number. I went straight to taking the inverse sine of it. But once you take the inverse sine of this, you get an angle of 7.96 degrees. As I said, this is at its messiest. I wouldn't expect you guys to be able to do this off the top of your head on an exam. It would take too long. As is, it took me a long time to do this. And I had the solutions in front of me. Doing these is a lot of jumping of logic, but it's just geometry. Going through and figuring out what angle is what. Any questions though?
Nope.
Let's do another one. I forget what's next. Other than clearing off all my drawings, getting rid of you, zooming back in. Next one's at least shorter, much shorter. A plastic light pipe. It's a fancy way of saying a fiber optic. By fancy, I mean the exact opposite of fancy. A plastic light pipe has an index refraction of 1.53. For total internal reflection, what is the minimum angle of incidence if it's an ale, which is n equals 1, and waddle? Okay, if you want to find the minimum angle, that's the critical angle. And it's always the inverse sine of n2 over n1. And we're going to be coming from inside the pipe to outside the pipe. And so for the first one, n2 will be ale. For the second one, if it's in waddle, n2 will be waddle. And that's kind of it. They're not all complicated. I think it's to make up for the last one. I'll do one more. This last one is one of those things that you sometimes wonder what is wrong with people who write physics textbooks. Like, seriously, there's enough wrong with me that I can question this, but like, the type of shit people make problems out of is really weird. And here's one of them saying a jewel thief hides a diamond by placing it at the bottom of a public swimming pool. He places a circular raft on the surface of the water directly above and centered over the diamond. If the surface of water is calm and the pool is 2 meters deep, find the minimal diameter of the raft to prevent the diamond from ever being seen. This is assuming the raft is never moving. No one's in the water. Like, there's a lot wrong with this problem. But let's just go for it anyways. See, if they want to find the minimum angle so that no one can ever see it, what we want to say is if someone looks at this, light's going to come from the diamond out, and that's how you see things. And we want to make it so that any angle over here is past the critical angle. We're going to make the minimum angle to be right here. That the distance over is the radius of this raft. Now, before I can even figure out what that is, if I want to make it so you can't see the diamond, that means the little angle down here, whoop, that must be the critical angle. Because if that's the critical angle, no matter how, and the raft matches that critical angle, you won't be able to see the underneath it. Because light from the diamond, if that's the critical angle, light from the diamond at this angle would bounce and stay in, be totally internally reflected, and so on. That light from the diamond reaching your eyes would only be visible if this is the critical angle within this range, completely blocked by our raft. And so we're going to say the critical angle, which is the inverse sine of n2 over n1. If we don't want anyone to see this, and it's in waddle, that must be when we're at going from into air from waddle. And that corresponds to 48.8 degrees. And that's going to be this little angle I marked, which I'm just going to draw this big O. Now, we know the depth of the pool is 2 meters. That's this depth from here to here. This is 2 meters. Well, if I soak a toe of this bitch, the tangent of an angle is opposite over adjacent. And that means the tangent of the angle is whatever this distance R is over that 2 meters. And so 2 meters times the tangent of the angle equals the radius, or 2 meters times the tangent of 48.8 degrees equals R. And doing that math, we can find that that is, really? I did that? 2.28 meters. And therefore the diameter of the raft, because this is only half the raft, right, is 4.56 meters. And that's it. That's really all I have for today. These problems are not that difficult, mostly because the equations involved are very simple. I just stabbed myself with a pen. But that's the general idea. Sound good?
Yep.
Okay. I'm going to stop there. The homework is all on this stuff. There is a bit of geometry. You might need to draw some stuff, but none of it gets too complicated. Yeah. Have a good weekend.
Yeah, you too.